All right, let's kick it off. Hopefully, I can remember how to do this. Yeah, so welcome everyone to the July meeting of the Central Florida Astronomical Society. And for anyone watching who hasn't joined yet and is not yet a member, why would you join? What are you waiting for? What's wrong with you? Come on, get with the program. We have many member benefits to offer you: access to private events and dark sky viewing locations. Yes, there are dark sky sites in Central Florida. We have a lunar telescope program, very vibrant. So if you want to try before you buy and get your hands on some gear and get a feel for the night sky, we can do that for you for free. We also have a vibrant online community via the groups.io platform, quarterly meetings at the Seminole State Planetarium, which is the coolest place to have an astronomy meeting. Your membership also includes membership in the Astronomical League, including their quarterly Reflector magazine, and it will make you feel good because we're a nonprofit 501c3 organization 100% powered by volunteers, including myself. If you're interested in joining, head on over to cfas.org for membership options. Today's agenda, we are going to start off with our main speaker, Philip Plait, presenting Under Alien Skies, which is an awesome book, which is why he's here tonight. Followed by some club news, and we're going to unveil our new website, so stay tuned for that. And of course, our Astrophotography Showcase, showing the latest and greatest images from our members who have been all over the country this month. And with that, a little bit of housekeeping here. So if you do have questions for our guest tonight, please use the chat function in Zoom to submit those, and we'll get to as many as we can afterwards. If we have time, maybe we can do some live ones too. And please remember to stay muted during the presentation. If you want to talk over me later, that's cool. I don't care. But, let's be courteous and keep the mute button on for the next hour at least. If not, I'll have to get nasty. You don't want to see me when I'm nasty. With that, let's introduce our main speaker tonight. Phil Plait. You've seen him on TV on How the Universe Works. You've seen him on the web on the Crash Course Astronomy series. You've read his stuff on Sci-Fi and Scientific American, and now on his newsletter, the Bad Astronomy newsletter on Beehive. And tonight, he's here with us presenting Under Alien Skies. Phil Plait, thank you so much for joining us here tonight.
Thank you, Frank, and everybody at FCAS, or CFAS, sorry, got that
Yes.
a little backwards. And I think I'm going to have to lower my voice after that introduction. You have a great voice for radio.
Thank you.
Um, so yeah, it's nice to be back. I'm glad to be anywhere right now. Just to let you all know, I was just talking to Frank about this. We just got pounded by rain, and it's going to happen again sometime during my talk. And so if I suddenly go away, that's why. We don't typically lose power, but we might. I've written several books, which is just weird. It's just weird. I'm not the kind of person, anytime my friends would say, you wrote a book? It doesn't seem like I'm the kind of person who could actually sit down and do that. And yet I've done it 4 times now. And this one, my latest book, as Frank was saying, is Under Alien Skies. Let me get my finger out of the way. And the idea here was, I was writing for Astronomy Magazine in the 90s, in the mid 90s, something like that. And I was trying to come up with ideas for articles, and I thought, what would be funny would be to write an article as if you were standing on a planet in an interesting place, and the sun sets, the sky gets dark, and then what do you see? And I wrote about, for example, being in a globular cluster, being in a nebula, and being near now, I'm maybe confusing 2 articles. A red giant star? It might have been a red dwarf star. The idea being that, you're all astronomers too. You know what it's like. I mean, we're left and right are reversed. This is my telescope. I have an 8-inch SCT. Haven't used it in a little while, but I've been known to, be on the sidewalk growing up, and then in college and all of that, looking at stuff and having people come up and talking to me about it. And you've probably had the question, what would this look like if I were there? You're showing them a planet or a galaxy or something. It's like, what would it look like if I were there? And it's actually not always easy to answer that question. Sometimes it's obvious. If you're on the moon or you're looking at the moon, it's the moon. It's going to look like the moon. But if you're inside a nebula, like the Orion Nebula, it's not at all obvious what it's going to look like. And even beyond sort of just the physics of it, you're seeing things up close that you may not be familiar with, and things you might not even think of. So it's like, what's it like to be on a planet orbiting a binary star? You're on Tatooine from Star Wars, and there are 2 stars in the sky. What is that like? What's the weather on that planet like? Or you're orbiting a red dwarf in a planet that's locked to the stars, that one side always faces the star, just like the moon does that with the Earth. And it turns out interesting things. It's not, again, you'd think, well, the sun's always up in the sky. And it's like, well, yeah, but there's a lot more going on. So I did all the math and science, did all the notes and everything, and didn't put any of the math in the book. But that's what the book is all about. And it's 10 different places I wanted to see up close. What would you be like? What would it be like if you were there? And so for this talk tonight, I picked one. And in some ways, it was hard to pick because all the places I write about, being on an asteroid, being in a nebula, in a globular cluster, my God, the views are extraordinary, and it would just be so cool to talk about them. But honestly, the flip side of that is picking one was super easy because there is just one place that I'd want to see up close of all the places in the universe. And I get this question a lot. Ooh, did you hear that? Thunder? Okay. Awesome. I'll talk faster. The people would ask me, sometimes I would be doing interviews for the book or whatever. I'd do Q&A after a talk, and people would say, what is the chapter you had the most fun writing? And it was Saturn. It's Saturn. I mean, you've all seen it. You all know what happens when somebody who's never looked through a telescope before comes up to the eyepiece and sees Saturn for the first time. That's what got me started to being an astronomer when I was like 5 years old, and an old crappy Tasco 3-inch telescope. I can't even remember now. It disintegrated years ago. If you all even remember Tasco telescopes, department store piece of junk. But good enough, right, to see Saturn's rings. And that hooked me. And so writing that chapter was great. The hardest part about writing that chapter was keeping it to 8,000 words, which is what a typical chapter is. I kept cutting it back, and it was still coming in super long. I could have easily written 20,000 words. So with that, let's see, I need to screen share. I will actually start my talk. Do this, and do that, and do this. So you should be seeing, you see the screen? Can you see it, Frank? Okay, great.
Yes.
So, let us say that you are on a ship, a cruise ship, not maybe the Enterprise, but something like that. And you're on your way to Saturn. You have booked your tickets, and it has cost you quite a pretty penny, but it is it's a trip of a lifetime. What are you going to see? Well, as you're approaching Saturn, you're not going to see much at first, right? You all know what this is like. Saturn, when it was first discovered, not when it was first discovered, when it was first seen before the invention of the telescope, was just a faint planet, right? Moving around in the sky very slowly. And then as telescopes were pointed towards it, like Galileo, I believe it was, who said that Saturn has ears, has two extensions on either side. And as telescopes got better, Euler, it was either Cassini or Euler, took a look at it and said, yeah, this thing is not touching Saturn at any point. It is something around the planet, a ring system. It wasn't clear what it was. I think Euler said it might be a liquid. But then it turns out, no, it's the rings are made of ice particles, and they have to be because the inner part of the ring system is orbiting Saturn much more rapidly than the outer part, right? Things closer to a planet are moving around faster. Anything solid that size would get torn apart. So it must be something that isn't solid. And as you're approaching Saturn, oh, dang it, I took too long. As Saturn grows in the view screen, at some point, it resolves itself, and the captain shows you the view as you're approaching. And we're coming in from an angle so that we can see the North Pole. We're coming in sort of down from above Saturn, and this is pretty much what you would see from there. This is I'll break the fourth wall here and say this is from Damian Peach, if you're familiar with him. He takes phenomenal images of Saturn and Jupiter and some deep space objects, not many, but his planetary imaging is just amazing. And so here's an image he took with a co-conspirator, and you can see Saturn here, and it's got this magnificent ring system. And the planet itself, too, it's kind of an interesting thing, and we're going to talk about that. Things you can see on Saturn, as well as inside it as well. But this would be a telescopic view. At this point, we're still millions of kilometers away from Saturn, and the view is still maybe a little bit fuzzy. You're not getting a great shot of it, even through the ship telescopes. And that's because if you're going to Saturn, you're not just going to a planet. You're going to a planet that has hundreds of moons. I'm not even sure what the count is. I think it's over 150, depending on what you call a moon, right? The biggest one is very, very large. Spoilers, right? And the smallest ones that have been discovered so far from Earth are a kilometer across, half a mile, something like that. And at Saturn's distance, which is a billion kilometers or more, these moons are very faint. And so they're very, very difficult to discover. A lot of clever methods to find these fainter and fainter objects astronomically. But at what point do you stop calling it a moon and you just start calling it, I don't even know, just crap that's floating out there orbiting Saturn. But the big ones are interesting. And that's one of the reasons I love Saturn so much, is that its moon system is bizarre. A handful of the moons are similar to each other, but honestly, the big ones are mostly each one is extremely different. And so as you're approaching Saturn, the captain, of course, plots a course that is going to take you past some of these interesting moons. So we're going to pass by some moons before we get to Saturn. So let's take a look. The first one we pass by is Iapetus. Iapetus, a few hundred kilometers across. It's not nearly as big as our moon. And it's strange, right? It's got a lot of craters on it. It's basically mostly ice and rock. Most of the moons of Saturn are very low density. They're mostly rock and water ice. Some of them are almost pure water ice, as we'll see. And they're covered in craters because that's just what happens when you're out, out in the outer solar system. You don't have an atmosphere to protect you. Even the smallest incoming bit of junk is going to slam into the surface and carve out a crater. As you'll see, most of the moons of Saturn have one really big crater, and that's not actually a coincidence, as I'll talk about in a minute. The thing about Iapetus, there are two things about Iapetus that are very weird. You can see that gigantic brown spot there on the right. It turns out that Iapetus is a two-faced moon, and sorry, I hit my space bar by accident. One side is really dark and one side is really bright. And this was known for a long time before we even sent probes to Iapetus, because it, like every other moon in the solar system, it is tidally locked to its host planet. So it spins once for every time it goes around, just like Earth's moon does. And so it only shows one face to the planet. But what that means is, as it's orbiting Saturn, as it's approaching the Earth, we see one hemisphere of it called the leading hemisphere. And as it goes around Saturn and then is moving to the other side, we see the other half of it called the trailing hemisphere. And even back in the day, a couple hundred years ago, they could tell, the astronomers of the day could tell that one side was darker than the other because the moon was faint when it was on one side of Saturn and bright when it was on the other. So what's going on there? I'll show you that in a sec. That's one weird thing. The other weird thing is, it's a little bit difficult to see here, but now in this next picture, it's a little more obvious. Iapetus is a walnut. It is a gigantic space walnut. What? This still kills me. When the first images came back from the Cassini space probe, everything was so odd, but Iapetus was so strange because it's got this huge mountainous ridge going exactly along its equator. That's ice there at the top, at the pole, and rock to the south of it, and then this ridge, and this ridge is bizarre. These mountains are 12 to 20 kilometers high, so 8 miles high. What is that? 40,000 feet. So taller than any mountain on Earth, and the ridge itself slopes out and is a couple of 100 kilometers wide. I'm sorry I use metric. It doesn't matter. Divide by 2, it's close enough. It's 100 and something miles wide. So this is a huge thing, and it goes all the way around the moon. What could have caused this? It's not clear. There are a lot of ideas. One is that when Iapetus formed, the material came together, and it was probably liquid. And as it cooled, it shrank. And the outer crust didn't shrink as much as the interior, and so it started to sort of push out at the equator. That probably is not correct. There's some physics that supports it and some physics that contradicts it. Another idea is it got whacked hard by an asteroid or another moon, and this blasted material off into space around it, and that coalesced to form a ring. And then eventually, because of the gravity interaction of Saturn, that ring collapsed down onto the moon. And it would kind of naturally do this exactly over the equator. The thing is, it would take a vast amount of material to do this, and it's unclear if that would just work. If you could have an impact that would do this and collapse back down on the moon and create a ridge this high all the way around. Maybe, but nobody really knows, and so it's kind of a mystery. Oh. And I'm sorry, and I was going to show you 2 pictures of the moon. I don't have them here. I apologize for that. But this other mystery is that one side of Iapetus is very bright and the other one's very dark, and that's not clear why either. It was thought for a while that another moon of Saturn is very dusty and dark, and it gets whacked by asteroids and micrometeorites, and that blasts dust into space, and that stuff can then coalesce onto Iapetus. But then, why is it only on one hemisphere, not the other? Maybe that has to do with the orbital motion of Iapetus. Not clear. Another idea is that there's dark material, and on the surface, there's just a mix of different materials on the surface of these moons, as we'll see. And if it's covered in ice, if there's a lot of ice on the surface and there's a dark bit, that'll absorb a little bit more sunlight. It'll warm up. Not much. The average temperature out there is extraordinarily cold. But it may be enough to turn ice directly into a gas very, very slowly. And so what happens is if you have a dark spot, the ice around it will start to turn into a gas and then move around the moon and move around to the other side where it will then coalesce and freeze out on the surface. And over time, it's a self-reinforcing positive feedback loop, and these dark spots will grow until all the ice forms onto the other side. And it kind of stops there because at that point the ice is so thick, I think. I've read some papers on this and it's not clear how this works, but at that point the ice is so thick that it stops sublimating. You can't get to the dark stuff underneath it. Nobody knows. This is still a mystery to this day, despite having so many close-up shots, and of course, being in a spaceship visiting Iapetus. Iapetus is quite a ways out from Saturn, well over 1 million kilometers, and its orbit is tipped a lot to Saturn's equator. That's also a third unusual thing, because all the other moons are pretty much in the plane, most of them are in the plane of Saturn's equator. And so there are 3 sort of mysteries about this. And when you have multiple mysteries about something, usually they're related. There's like 1 or 2 things that happen that connect them, but nobody really knows. And tilting a moon, an impact that could tilt it that much, would probably vaporize it. It's really hard to get an object to change the inclination of its orbit. So it's unclear how that all works. Okay, so now our ship is diving down, and we're going to get into the plane of the rings. And as we approach Saturn now, we're over Saturn's equator, and there are 3 things to see in this picture. 1, lots of moons. Big fuzzy peach of a moon on the left, that's Titan. We're going to see that up close in a few minutes. And on the right, there are several other moons you can see just above and below the plane of the rings. Most of the moons orbit very, very close to the plane of those rings, but not exactly. And that turns out to be important, and that's more foreshadowing. At some point, I will be done foreshadowing, but there's a lot of cool stuff to go here. A second thing is that, of course, we're seeing the rings edge on. And when I talk to people in the public, and I show them pictures of Saturn, or they see it through a telescope, and I tell them, these rings are something like 250, 280,000 kilometers across. So from end to end, if you were to put one end of Saturn's rings at the surface of the Earth, the other end would extend about 2/3 of the way to the moon. So these are immense structures. They are huge. But the question is, how thick are they, right? And so, I mean, thickness up and down. And I ask people, how thick do you think they are? And they're like, oh, I don't know, 1,000 miles, 100 miles, whatever. And in some places, they are so narrow, they're like a kilometer or less. And sometimes they're so thin, they're only 10 to 20 meters high. And that is, a 3-story building, 4, 5, 6-story building. And yet, you're talking about an object that is hundreds of thousand object, a structure, 100,000 miles, in radius, that is only, 20 meters thick. That's so strange. Why is that? And it turns out that's not a coincidence. Of course, it can't be. There's no way that could be a coincidence. I should say that to scale, Saturn's rings are thinner than a piece of paper. If you took an 8.5 by 11 piece of paper, right, and scaled it up to the size of Saturn's rings, the paper would be thicker, a lot thicker. So Saturn's rings are incredibly thin. Why? And it turns out that probably we know that the rings are made up of countless ice particles, as we'll see, and they're all orbiting Saturn in their own independent orbits. The likely explanation, the amount of mass in the rings, and we know that they're losing mass over time, little impacts vaporize material and it blasts away and everything, and that the rings are probably getting smaller over time. I mean, they're losing material. If you trace that backwards, they're probably less than 400 million years old. And they're certainly less than 400 million years old, and they may be less than 200 million years old, which means that if you were a dinosaur astronomer on Earth and looked at Saturn, you may not have seen the rings. They may not have existed yet. What probably happened is a small moon or two moons collided, icy moons, smacked into each other and basically blew themselves apart. That would create a sort of a thick disk around Saturn. And if it were tilted with respect to Saturn's equator, its gravity would actually sort of force that material to become over the equator. It's just tides. It's the same thing that makes the moon orbit, again, one face always pointing towards the Earth. It's the same thing that raises the tides on Earth every day and lowers them. And that's a complicated process, and I won't go into it now. But over time, Saturn's tides would flatten it. And one of the reasons this works so efficiently is the other weird thing about this picture. And that is when you look at Saturn, it's not circular, and it's not even close to being a circle. When you notice it, it's flat. The technical term is oblate. It's a flattened spheroid, like a beach ball that somebody's sitting on, right, squishing it. And there are two reasons for this. One is that Saturn is very low density. The Earth has a density of about 5.5 times that of water. We have an iron core that is surrounded by a mantle made of rock, and our crust, which is very thin, that's also made of rock. And so Earth is very, very dense. And when you average over the whole planet, we're 5.5 times denser than water, 5.5 grams per cubic centimeter. So if you had a cubic centimeter like the size of a 6-sided die or a sugar cube, that would weigh 1 gram if it were made of water. If it were made of average Earth, it would weigh 5.5 grams. Well, it turns out gas giants like Jupiter have a density very close to 1 because they're gas giants. They do have cores which are very dense, but they have thousands and thousands of kilometers of liquid in them that kind of merges into a gas as you get higher and higher up away from the core. And then you have this tremendous atmosphere which goes down a long way. Gas is much less dense than water. And so the average of these planets, Jupiter, Uranus, Neptune, is about 1. They're about as average, about the same density as water. Saturn is actually less dense than water. And so the old joke is, and I'm sure you've all heard this, if you threw it into a bathtub, it would float, but it would leave a ring. And if you haven't heard that, shame on you. I remember hearing that when I was a kid. But there you go. It's just very, very low density. That's one reason it's oblate. That's a part of the reason, but not the reason. The reason is Saturn spins very, very rapidly. A single day on Saturn, very roughly 10 hours. So its rotational rate is 2.5 times faster than Earth. But it's also very, very big. It's 10 times Earth's diameter, 9.5. So it's this huge planet spinning very rapidly. And so there's a very, very strong centrifugal force at the equator, which makes it want to expand away at the equator. It's the same force that you feel like on a merry-go-round or when you're in a car and you take a quick turn and you're thrown to the outside of that turn. And I know the physics. A lot of people say that's not really a force. It is. I'm not going to get into that here. They say it's fictitious. That's not a great name to call it. It's a real force. But it's basically, you can think of it as a force outward. And because Saturn is rotating at the poles, it's not rotating very much. So there's not much of an outward force, but at the equator, it's really moving around, right, in this huge circle. So there's a huge force outward. And because Saturn is so low density, it can really stretch out. If it were made of, iron, you'd barely be able to see that it's not a sphere. But because it's made of these low density gases, it's really, really oblate, and it's very obvious. And once you know that, it's easier to notice through a telescope. And in fact, right now, we're getting close to Saturn's to Earth being in the plane of Saturn's rings. Our orbits are a little bit tilted, and Saturn is tipped to the sun by about the same amount the Earth is, about 24, 25 degrees. And so sometimes we see those rings at a great angle, and like in Damien's picture, and you get this gorgeous system. And other times we see them edge on, and we're approaching that season. I want to say it's next year. The Saturn's rings will be edge on, and so you're just going to see this thin line. Astronomers, planetary scientists love that because we can learn a lot about the rings when they're edge on, that you can't tell, like, if there's any deviation from it being perfectly flat, and it turns out there are, as we'll see. So there you go. When Saturn's rings are going to be edge on, you'll be able to notice how oblate Saturn is at your eyepiece, and I recommend you do that because it's awesome. Right now it's up at 5 in the morning. Who's going to do that? But next year I think it'll be better. Okay, fine. So obviously I like Saturn. I could literally just talk about it for hours and hours. I will spare you. And now we're in our spaceship, and we're back in the ship, and we're looking out, and we're heading in towards the planet, and we're going to pass by some other moons. I keep forgetting. There's more to see about Saturn. I don't know if you remember. This is an image the Cassini spacecraft took, or you're seeing it out your viewport. Take your pick. And you can see the rings are casting a shadow on the planet. And that thing in the northern hemisphere is a storm. It erupted in 2010. It was actually discovered on Earth. I want to say it was Christopher Goh, an amateur astronomer, who spotted it and then announced it. And then NASA scientists were like, "Oh, we should look at this with our orbiter." And they pointed Cassini at it. And it's basically a bubble of material that came up from Saturn's warmer interior and erupted out through the top of the atmosphere. And it was this immense storm. And over the next few months, the winds around Saturn wrapped it all the way around the planet. You can see the storm, extending off to the right there, going all the way around the planet, and then you can see that tail. It's much fainter, but you can see it wrapping around all the way. Unwrapped, that thing would almost extend from the Earth to the moon. So it's that storm is, just the head of it is bigger than Earth, and that whole thing wraps around. So there's plenty to see on Saturn. There's still lots of moons to see as well. This is one of my favorite moons in the solar system, Hyperion. A lot of these moons are small. And because of that, they don't have much gravity. Now, if you take something that's really, really big, like the size of Earth's moon, and you try to stretch it and make it really oblong, like a potato, its gravity will try to crush it back into a sphere. Another way to think of this is, you could imagine if you have a pile of sand on Earth, and you just start pouring sand onto a pile. At some point, that sand is going to start spreading out, and it won't let you pile it up any higher. Anytime you try to do that, it just collapses out. And that's just because of gravity. Gravity is trying to make everything form into a sphere. And if you have a small moon, there's not much gravity. And so you can have these really strangely shaped objects. And it turns out most objects under 400 kilometers across, roughly, at that point, that's where you start getting enough gravity to make yourself a sphere. Anything smaller than that can be all kinds of wacky shapes. And in this case, potato shape, very common for large asteroids and moons. And so Hyperion is an example of this. And there are 2, 3, maybe very strange things about this moon. And they're all related. One is that if you can look in the craters there, you can see lots of dark patches. This is material that's called tholins. Tholins are complex organic molecules. So these are carbon-based molecules that are very complicated. And they're made, if you take simple stuff like methane. Methane is just one carbon atom with 4 hydrogens stuck on it, really simple. Hit it with ultraviolet light, it breaks apart, and then the methane can reform into more and more complex carbon-based molecules. And that's how you can get a lot of what we call organic stuff, like tholins. Tholins, depending on how they're made, can be red or orange or yellow or brown or black. You've seen pictures of Pluto and it's kind of reddish. Those are tholins on the surface. It's methane that got hit by sunlight. Ultraviolet light from the sun breaks it apart, makes more complicated stuff. So there's this material in these craters, and it flows down into the bottom of the crater and makes the crater look very black. Now, what's weird about these craters is that black shows you that the floors of these craters are quite flat. These are not deep craters. They're actually, excuse me, I may be saying this backwards. Excuse me, I said that exactly wrong. The craters are actually very steep walled. I'm sorry, I was thinking about another moon. And you don't get that with rock. And even ice, a lot of the times, you look at craters, they're bowl shaped or they're flat at the bottom. And so these craters are oddly shaped. And then when you notice that this part of Hyperion is dominated by a gigantic crater, and you can see it extends almost all the way to the upper right and upper left. And it's this immense, when they get that big, we call them basins. And it's huge. It's almost the size of the whole moon. So something big whacked into Hyperion really hard. The thing is, you can't get a crater that big on a chunk of solid ice or a chunk of solid rock. If you get a crater that is, an impact can only make a crater up to a certain size before you disrupt the moon. An impact any faster or from an object any bigger would literally shatter the moon. Now, sometimes they'll break apart and then recoalesce, and we see that a lot. But then the craters are all erased. But in this case, this thing's got tons of craters, and yet it has this immense impact. How is that possible? And the answer is, it's not solid. Hyperion is extremely low density. It looks like styrofoam, and that's because it kind of is. It's made of ice. It's very likely that it has suffered so many impacts and has been blown apart and recoalesced that it's not solid anymore. It's a rubble pile. It's made up of trillions and trillions of individual pieces of ice and a little bit of rock. And so now, imagine you've got a big box of styrofoam peanuts and you punch it. What happens? Well, the peanuts fly around and you pull your hand back and they settle back down, and you might get a shallow big crater, but that's it. It's not going to be very deep like that. That's what happens when you have a big impact on Hyperion. It absorbs that impact, so you can't shatter the moon anymore. A big enough impact could, but in this case, it was a big impact, but not quite enough to blow it apart, but it still left this immense crater on it. So yeah, top to bottom, this is a very, very strange moon. All right, speaking of strange moons, moving on. Now we're approaching Titan. Titan was known to be weird for a long time. It's yellowish, and through big telescopes, it's fuzzy looking. No surface features to be seen. That's almost literally impossible for a moon to not have any surface features at all. And the reason for that, as you likely all know, is because it has an atmosphere. It's a very, very thick atmosphere. Titan is huge. It's actually roughly the size of Mercury. If it were in the inner solar system, we'd call it a planet. It's smaller than the Earth, so it has lower gravity. It's got a lot of rock and ice in its surface, but it also has this thick atmosphere, which is roughly 1.5 times denser than Earth's atmosphere. So if you were standing on the surface of Titan, you'd be dead. Sorry, it's extremely cold there, and so that would kill you very, very quickly. And the atmosphere is also, even if it were warm, is unbreathable. It's mostly nitrogen, which is kind of interesting because our atmosphere is mostly nitrogen, 78% nitrogen. Titan's is more like 98%, something like that. I don't know the exact number, but it is mostly nitrogen. And if you were standing there, the amount of air around you would be very similar to the amount of air you have here. If you were going to try to run on Titan, you'd have lower gravity, but sort of the wind on your face would feel the same. Of course, it would kill you. But there you go. It has a lot of atmosphere. Not clear why. It may simply be that it just has enough gravity to hold on to an atmosphere. On the other hand, Ganymede, the largest moon of Jupiter, roughly the same size, does not have an atmosphere. So that's an interesting question. Why does one have one and the other one doesn't? But this atmosphere is mostly nitrogen and a little bit of methane. Those are transparent. So why can't we see through it? And the answer is smog. It's those tholins again. The methane in Titan's atmosphere has been hit by ultraviolet light, broken down, recombines, forms basically an orange smog, a haze, over the entire moon, and that is quite opaque, and so you can't see the surface. If you look at the top of Titan there, you can kind of see a bluish cap. If you look at the top, it's like there's this little haze layer at the top. That's real. It's called the Titan polar cap, and that's a different haze layer that exists above the thick part of the atmosphere, and so it can be seen. The thing is, not all kinds of light are the same. This atmosphere is opaque to visible light, the kind we see. However, infrared light can pierce material like this. So if you have an infrared camera, for example, you can actually see features on Saturn. So if our captain switches from visible light to infrared light, ooh, suddenly you see this. And I remember when these pictures came in, I thought I was looking at Mars. It really looks like Mars, doesn't it? But that is Titan seen in infrared. And now features on the surface, we can see them because the infrared light from them reflected from the sun can get out of the atmosphere. And we can see that there are these dark regions all along the equator of Titan. And it turns out these are hydrocarbon fields. So complex carbon and hydrogen molecules, hydrocarbons, gasoline is a hydrocarbon, for example, but it's frozen. And it turns out they're in tiny little grains along the surface of Titan. Titan has an atmosphere, it also has winds. They're not strong, but they're there, and it can blow, it erodes the rocks that are there, these rocks made of hydrocarbon, and they break down into grains. The winds blow them into dunes. And so if you were to see these patches up really close, you would see rippling sand dunes across them, which is just phenomenal to think, this moon, a billion kilometers from the sun, has a lot of features that, on paper seem kind of Earth-like. And there's another one too. Cassini, the spacecraft, had radar on it. It had a radio transmitter that it could beam radio pulses down to Titan and let them bounce back up. And what you can do then is measure the topography of the moon. So if you have a mountain, for example, your radio wave hits that mountain and bounces back and takes less time because it's a shorter distance for it to get there and back to Cassini than, say, a valley. And so if you can time these pulses, you can create a map, a topographical map of the moon. You find out it's mostly flat. However, at the poles, there are highlands. It's hilly. Wouldn't call it mountainous, but there are a lot of hills up there, and it's kind of rough terrain. But there's something else. Here's a radar map of Titan's near its north pole, and you can see down at the bottom all those ridges and everything. It's very, very hilly. But then there's this weird black thing. And it's like, what is that? And it's like, well, the reason it's black is because whatever is there is absorbing radar. What absorbs radar and doesn't reflect it? And the answer is liquid. Liquid absorbs radar. And so what you're seeing here is a vast lake of liquid methane and some liquid ethane, which is a little bit more complex than methane. And I mean, look at it. Once you realize it's a lake, you're like, of course. Look at the bottom there. There are creeks and tributaries that flow into rivers, and then they flow. As they flow downhill, they all merge together and then form this gigantic lake. Titan has a methane cycle. I mean, you remember Earth science in like middle school, and you learn about Earth's water cycle. You have, say, a lake, and in the summer that water evaporates, it turns into water vapor, goes into the air. Rains out onto the hills, and then that water then trickles down through creeks and tributaries and everything and flows back into the lake. That's happening on Titan, except it's methane. This water cycle on Earth is great because, first of all, it transports water from one place to another, which is good. I mean, it's raining where I am, and I can still hear the thunder going. So that's good, right? But also, it mixes up minerals in the ground and brings them to a lake and concentrates them. And that is possible that is what helps life arise. You've now got all these complex minerals and everything. You've got water to suspend them in, maybe an energy source like sunlight. It makes simple molecules more complicated, and eventually maybe they get complicated enough to start reproducing. And we don't know how that works. And is it happening on Titan? Don't know. Are there little alien fishies swimming in methane ocean or lakes on Titan? We don't know. But that's phenomenal. Again, yet another Earth-like aspect to a weird moon 1 billion kilometers away. Moving on, another one of my favorite moons. This is Enceladus. Now, Enceladus is a few hundred kilometers across. It's not very big. It's mostly round. It's a little bit egg-shaped, not much. And it's almost 100% water ice, which is why it looks so white in this image. Now, the thing about this image is that the northern hemisphere has lots of craters in it, but the southern hemisphere doesn't. And this was a big surprise. Nobody was expecting an airless moon to not have craters. Why doesn't it have craters? Well, I will direct your attention to those long stripes on the bottom, like a tiger clawed it. And these are called the tiger stripes. And when I first heard that, I thought, oh yeah, it's like a tiger claw. And it's like, no, it's actually like the stripes on a tiger, of course. What are those? Those were very strange. Well, when Cassini went past Enceladus and turned around, and it flew over sort of the dark side, the side of Enceladus facing away from the sun, and then turned back to look at the dark side to take images, it was seeing the moon backlit, and what it saw was this. These are geysers of water shooting up into space. And this was, I shouldn't say it's completely unexpected, because we knew that there were forces that could create liquid water in these moons. Jupiter's moon Europa, we know, has liquid water under its surface. And so we figured that was going to happen with Saturn's moons as well. But the idea of there being geysers, that was a surprise. And there are over 100 individual geysers. And they're coming from these cracks. These are called sulcus, which means chasm. It means groove. And in Latin, I think it is, and the plural is sulci, S-U-L-C-I. These are cracks in Enceladus, and its orbit is not perfectly circular around Saturn. Sometimes it's a little bit farther away, sometimes a little bit closer. And the gravity is changing, and so sometimes it's being compressed and sometimes it's being extended. And as it does that, there's friction being generated inside the moon, because you're working it, right? You're making it, you're squeezing it, extending it, squeezing, extending it. Enough friction is being generated to heat the interior of the moon and liquefy it. And so there's a liquid water ocean under the surface. That's probably what's happening with Europa as well. But there are also these cracks, and the water is under pressure. It forces its way up and bursts out of the surface. And it turns out the activity of these geysers is related to where Enceladus is in its orbit around Saturn, kind of clinching the fact that it's the gravity of Saturn squeezing this moon that's making it erupt like this. I love this shot. You can see the plumes as they from the dark side of Enceladus, as they get high enough, they get up into the sunlight, and so you can see them. It's a phenomenal discovery, phenomenal image. And then finally, the last giant moon, the last big moon orbiting outside of Saturn's rings is Mimas. Also a few hundred kilometers across, saturated with craters. And of course, the nickname the Death Star moon, for obvious enough reasons. Looks like the Death Star from Star Wars. That crater called Herschel. Am I confusing that with Phobos? Yeah, no, I think this one's called Herschel, pretty sure, is huge. And again, it's about as big a crater as you can get on a moon without shattering it. And so that's why you see sort of a really big crater. If the crater were much bigger, there wouldn't be any craters left, because the moon would have been shattered. So on these moons, you do see sort of a largest crater like that. And it's immense. It's a fairly interesting moon. It's mostly water ice and rock. Very cool, because it looks like the Death Star. There's another moon, I want to say Tethys, that also has a gigantic crater that also makes it look like the Death Star, but nothing like Mimas. And so this is everybody's favorite moon to talk about on social media. And it's also the last big moon before we reach the rings. Saturn's rings have been known since the early 1600s. Galileo may or may not have discovered them. He certainly was self-aggrandizing. He didn't actually discover a lot of the stuff that people think he discovered, like Jupiter's moons and stuff. Probably somebody else did, but he was the one who really wrote down what was going on, kept track of what he was doing, and published his stuff, making him one of the first science communicators. And over the years, we started learning more about the rings. They're divided up into sections. It's not just one big ring, and they're named kind of in order of discovery. And I always get these mixed up. But I should probably look this up. If only I had a book in front of me to make sure that I do this right. Somewhere, if I pause to look this up, it's going to take 20 minutes. CBA. Yes. All right. I was right. The inner faint ring that you see there on the right. Now Saturn's off to the right in this image. The inner ring there is the C ring. The middle one, which is the brightest one, is the B ring, and the outer one is the A ring. So they're technically named in order of discovery. In this case, A, B, C. There's a D ring that's closer in that you can't really see here. There's also an E, F, and G ring that are outside, and they're all a little bit different. And which is interesting because that's telling you something is going on. As you get closer and closer to Saturn, the rings get thinner and thinner. That probably has to do with Saturn's gravity. There's a constant rain of particles coming down from the rings onto Saturn, and that's coming from the inner rings. That's probably why they're thinner. But there's less, the rings are almost pure water ice, like 98 or more percent pure water ice. The rest of it is basically dust. It's rock dust, silicates. And that changes sort of the color of them. And so for some reason, the B ring, a little bit more reflective than the A ring, which has a little bit more dust in the rings. And as you can see, there are gaps between them. You can see the Cassini division there between the A and B ring, which for a long time was thought to be empty. But it's not. There are ringlets in it. And then the Encke ring, named after an astronomer, the next big gap. And then right at the edge, there's a very thin ring called the Keeler gap. A gap called the Keeler gap. And we'll be taking a trip into that in just a moment. What causes these rings? Well, it was first thought that maybe there were moons in there that were just basically plowing into the material and drawing it in. It turns out that doesn't work, usually. What's actually happening is, mostly this is due to Mimas. As Mimas goes around Saturn, the rings are actually moving around much faster. The particles in the rings are moving around faster because they're closer to Saturn. If a particle goes around twice for every once Mimas goes around, then you get sort of Saturn and that particle and Mimas aligned at the same time. And this is called a resonance. And any simple fraction, you can have 2 to 1, 3 to 2, 5 to 4, anything like that. Pumps energy into the ring particles. It's very similar physics to if you're on a playground swing and you kick your legs, right, to get up higher. If you kick your legs when you're going up and pull them in when you're going down, that gives you more and more energy and you can swing higher and higher. Very similar physics going on here. So Mimas actually pulls out ring particles, and they change when they move away from Saturn, they slow down, and so they basically just don't go back into that gap, and you just pull the particles out. And all of these big gaps are simple resonances with the moons of Saturn. That's why they're, and it turns out there are thousands of these ringlets because there are lots and lots of different resonances going on. Here's a close-up of the outer part of the A ring. And the outer part of the B ring there on the right, the Cassini division. I keep saying the wrong thing. I am sorry. On the right is the Encke gap. On the left is the Keeler gap. The Encke gap's a few hundred kilometers wide. The Keeler gap is only like 25 kilometers wide, so it's very narrow. And here you can see all the different ringlets. It kind of looks like an old phonograph record, right? Kind of cool. These like grooves. Get closer in. So now we're right looking straight down there on the Keeler gap. The Keeler gap, as Cassini was first orbiting there in the early 2000s, was so clear of material, people were saying, you know what? There may be a moonlet in there sweeping out stuff. helping, and so it's basically helping to clear everything out. And it was called the Keeler Moon for a while, and then finally it was discovered by Cassini, and you can see it right there in the center. This image was taken during the time when Saturn's rings were edge on to the sun. So any change in elevation would cast a really long shadow. And so this little tiny moon, which is like 8 kilometers across, 5 miles, it's not very big, is casting this really long shadow. But then if you look at it, it's like, well, what are those like scallopy things? There's, if you look, Saturn now is down to the left. To the lower right of the moon, you see there are the scalloping on the inside of the gap. On the outside of the gap, that's where the scallops are on the other side of the moon. What is going on? And they're very tall. These ripples are quite tall. You can see them casting a shadow there on the rings. Well, let's take a look. Here's a closer look at that moon. It looks like a pecan. That moon is called Daphnis. Daphnis, it turns out, is not much smaller than the gap of rings that it's in. And its orbit is just barely tilted to Saturn's rings. And by barely, I mean it's just a few kilometers. I mean, this thing orbits, let's see, it's on the outer part of the rings. It's over 100,000 kilometers from Saturn. And yet its orbit is only tilted by about 5 kilometers at most. So it rises as it orbits. On one side of its orbit, it's 5 kilometers above the plane of the rings, and the other side is 5 kilometers below, something like that. And it turns out that's what's making the scalloping. If you are a ring particle orbiting Saturn, and you're on the inside, closer to Saturn than Daphnis, as you orbit, you very slowly, you're moving at almost the same speed, so you very slowly approach Daphnis. Now, this is similar to being on a highway, and you're doing 101 kilometers an hour, and somebody in the right lane is doing 100, right? You're both moving very rapidly, but it seems like relatively you're only moving at 1 kilometer an hour, which is slower than walking speed. Same thing here. They're both going around Saturn at high speed, but their relative speeds are very low. And so as you approach Daphnis, as you come up to it, if it's above you, because it's, up in that part of its orbit, you're going to feel the tug up before you get to it, and then you pass it. I think I've got this right. And so the ripples lead, oh boy, I hope I've got this right. The ripples lead Daphnis in their orbit. On the other hand, if you're outside Daphnis, you're moving slower, and Daphnis approaches you, and so it pulls you up as it passes, and so that ripple now is it ripples up on the outside of that gap. And so you have these, the inner ripples lead Daphnis, the outer ripples trail it, and they get stronger the closer you get to the moon, because those are getting pulled the hardest right now. And eventually Saturn's gravity flattens them out again. And you can see that here. I believe we see Saturn's up, and so the inner gap is above it, and you can see that ripple starting. The outer part of the gap is now to the bottom of this image, and you can see the ripples trailing it. I hope I've explained that clearly. Now, what happens if we now get over the gap and start to come in towards Daphnis? This is what it looks like. I got it right. Look at that. There are the ripples, right, leading Daphnis. On the inner part, you can see Saturn there on the left, and the ripples are trailing it on the outside. And if we take our ship now and go into that gap, we can get this is artwork, but you can see what it would kind of look like waves in the ocean ahead of Daphnis and then trailing it behind there. And if we were to come up behind it and approach it, you would see these ripples like rippled candy in the rings. This would be, for my money, one of the coolest things you could ever see in your life. This would be so amazing. It would look very much like this. And now, if you turned and looked towards Saturn, right, the ring particles are now fairly close to you. And if you approach that sort of inner part of a gap, you will see that the rings are not solid at all, but they're made of these particles. Now, the thing is, even from relatively close, just a few kilometers away, you're not going to be able to see these individual particles because they are small. The biggest ones are maybe 10 meters wide, the size of a large room, like a small movie theater, something like that. They're not very big, and that's because anything big, gets hit constantly by these particles. It's slow speed collisions, But over time, right, they just chip away at each other. And so we don't have any close-up pictures of the rings now. But if we did, we would see that they're probably mostly rounded and smooth because they've basically been ground down over millions of years into these individual particles. And that's why Saturn's rings can be so flat, because the particles in them are very small. And so you don't get something that's very big to poke in and out of the rings unless there's some gravity of a moonlet like Daphnis pulling on it. So now our captain has taken us out through the Keeler gap, which you can see there in the outer ring. And now we're going to go over the pole of Saturn and down onto the night side. And as you look down on the planet, you can see its stripes. It's banded very much like Jupiter. Okay, I'm running out of time, so we're almost at the end here. It's banded very much like Jupiter, but the bands aren't as obvious. You've seen Saturn through a telescope. You've seen Jupiter through a telescope. Saturn's banding is much fainter, and that's because its atmosphere is full of haze. Again, you'll notice through the telescope that Saturn looks yellower than Jupiter does. That's because it has this haze of material, just like Titan does. And so seeing the banding is more difficult. But as you look down on the pole of Saturn, there's a very strange thing that was seen very clearly by Cassini, and that's the giant hexagon. Now this, of course, is the base that the aliens created to observe us. That would be a terrible base, right, on the pole of a planet. You'd never get a good view of Earth from there. It turns out that if you have an atmosphere on a rotating planet and winds, near the poles, you can naturally generate regular geometric shapes. It's similar to the Earth's jet stream, this vortex around the pole, the polar vortex. If you have conditions that are a little bit different than Earth, like no surface, Saturn doesn't have a surface, it's just gas all the way down, right? And these winds blowing, the winds, any sort of an eddy, any kind of whirl that you create can amplify itself, turn in and basically turn into one of these angled turns. And you just see these regular hexagon shapes. They've been recreated in the lab. The fluid dynamics is unbelievably complicated, but these things arise naturally. Each side of this hexagon is just slightly bigger than Earth, to give you a sense of how immense this thing is. It's very, very large, about 2 Earths wide. And in the center of it is this gigantic cyclone, and it's a slightly different color. There are chemicals in there that are coloring it, and you can see dozens, 100 maybe, smaller little vortices, all these storms swirling around. Very strange, very, very peculiar place. Now we're going to go back down around Saturn, and we're now at the terminator, the twilight zone of Saturn, where the sun is starting to set. You can see Titan up there to the upper right. Its atmosphere scatters light, and so you see this ring around it, even though most of the moon is dark, similar to the Earth does this during a lunar eclipse, right? And the sunlight gets scattered through our atmosphere and turns red and lights up the moon. That's why the moon turns red. The atmosphere of Saturn there is starting to turn red, and the rings are still in sunlight, so they're still lit up, and we can see their shadow on the clouds itself. And as we go deeper into the twilight, this view shows part of the spaceship there on the left. You see those clouds turning red, and we're not quite over the equator. We're at slightly higher latitude, and so we get a good view of the rings at an angle there. Saturn rotates in 10 hours, so nighttime only lasts 5 hours. So sunset to midnight is only 2.5 hours. And that's interesting, because Saturn itself casts a shadow on those rings. And as Saturn rotates, you'll see that shadow rise. It'll be on the eastern horizon, say at twilight, and then at midnight, it'll be on your meridian due south, and then it'll set in the west, if I've thought that through correctly. I might have my directions backwards, doesn't matter. The point is that shadow will rise and set over the course of 5 hours. So if you are in a spaceship, or even better, a dirigible, a Zeppelin, you could actually be on Saturn in its atmosphere. The atmosphere gets thicker and thicker as you go down, but at some height above the cloud tops, The atmosphere is basically at 1 atmospheric pressure, just like it is on Earth. Now, it's very cold. It's hydrogen and helium and that sort of thing, but there's no oxygen. So if you had a tank of pressurized hydrogen, say, which is very easy to do, and you heat it up, you could create a balloon that would float in Saturn's atmosphere, and you can hang a gondola underneath it, pressurize it, heat it, and you could float above Saturn's atmosphere. Imagine what you could charge for that as a honeymoon suite on a dirigible floating in Saturn's atmosphere. And the beauty of that is that you could watch the shadow. Here's the shadow of Saturn across its rings at one point, and then you just wait an hour or two, and you'd see this. Depending on the time of year, you might see more of the rings blocked or less. But that would be phenomenal. And you can see that's Titan there on the right. The moon that's closer into the center, that's Enceladus. You can see some of the plumes there. The artist, Kevin Gill, I asked him to put this together for me for this talk, and he did that. He created these shadowy pictures. Unbelievable. Over the course of time, you'd watch these moons rise and set. They would rise and move across the sky much faster than Earth's moon does because of Saturn's rapid rotation. If you could hang out for many days, you would see them changing positions in the sky as they orbit around Saturn. If there's a better place to visit in the solar system, man. And yet there's still one more thing. We've gone over the day side, over the pole, into the night side, and now we're going to pull away, and we're going to go into the plane. We're not going to be in the plane of Saturn, but we're just going to pull away so that now Saturn is behind us. And we'll turn around and we'll look at the dark side of Saturn with the sun on the other side. And what do you see? This. This is one of the most famous astronomical pictures ever taken. Certainly the most famous one that Cassini did. This is a mosaic of many, many shots, individual shots. The sun is actually off to the side, but Saturn is very, very close to being in a line with the sun. We're seeing it backlit. Its atmosphere is scattering sunlight, so it's made that ring of light around the planet. We're seeing the rings backlit. So the sunlight is now passing through the rings and toward us. And that's funny because it switches the brightness. Now they're not just reflecting that light, they're transmitting it. And now the B ring is now brighter than the A ring, which is opposite sort of what it was before. And there are dark patches in there and all kinds of things just depending on how the light passes through. You can see an outer ring that's very narrow, and then a very diffuse ring, which is icy particles that are probably, I believe, broken off of the moon Phoebe, which orbits way, way out from Saturn. And it's distributing ice particles around it. What's interesting about this picture is if you zoom in to the lower right and you see that bright little star there, you can see a bunch of stars in the background, and then you can, the captain can say, as they always do in science fiction shows, "Computer, enhance," and you see this. That's the Earth and the moon, right? That's another reason to love this shot. 1 billion kilometers away, 600 million miles away, Cassini sees the Earth and our moon as a little blob off to the side there. And so that to me, scientifically, not of the utmost importance. As compared to everything else we've learned more about Saturn in the dozen years that Cassini orbited it than we had in the 400 years since the invention of the telescope. I would argue that. So the scientific value of this particular shot isn't much, but the visceral, the emotional impact of it, the philosophical impact of it is so strong, right? This urge that we have, no matter where we go, to turn around and look toward home is very strong. But it also shows just how far we've gotten and why we explore in the first place. We go to Saturn to see how alien it is, how weird it is, and yet we find atmospheres like our own, cold, but atmospheres like our own, liquid water, the potential for life. So many features harken back to our own planet. And then when we see it, every human being who has ever lived would fit in this shot for the moment. In a few years, who knows? But up to right now, they're all there. And you've probably all heard Carl Sagan's Pale Blue Dot. If you haven't, what are you doing? Go listen to that. Go find it on YouTube. And that to me says it all, as who we are as a species. We go to these places to explore and to learn and to compare and contrast them with our own world and learn more about where we come from and who we are. And that is why we do this. And that ends our tour. I have been your tour guide, Phil Plait. If you want to explore other parts of our interplanetary and interstellar cruise line, you can go to Pluto, the last sentinel of the solar system, a globular cluster where you can watch 1,000,000 stars rise and set, 1,000,000 sunrises and 1,000,000 sunsets every day. You can visit the Orion Nebula, the birthplace, the star factory, the birthplace of stars, or the last vacation you will ever take to a black hole. I have written the tour guide, ultimate sightseer's guide to all of these and more in Under Alien Skies, a sightseer's guide to the universe. Thank you very much for having me and bearing with me while I went over time a little bit. And if it's okay with you all, I'm happy to take questions. If we don't have time for that, that's fine as well. I will acquiesce to Frank.
Oh, thank you so much. Yeah. Yeah, we have a few questions here if you're up for it. And yeah,
Don't
just when
ask
you
me any
thought
details because I can never remember numbers and details.
none of them are like that, fortunately. But just for myself, I mean, like just when you thought Saturn couldn't get more awe-inspiring, and there you have it. It's even better than what you see through the scope. And thanks so much.
Yeah.
Those images are really cool, by the way. Like the book paints all these mental images that you kind of imagine as you're reading it, which is cool. But seeing those artistic renderings kind of makes it even more real. So I
Yeah,
enjoyed
those
that
are
a
those
lot.
are very cool, and there are lots of pictures. Well, there's a pictures in the book and diagrams because some of the stuff I didn't even talk about half the crap I learned about Saturn.
Mhm.
Pardon me. God, I hope I have the hiccups now. Wouldn't that be great? There's all kinds of things going on in the rings. All these weird features, propellers and propeller shaped like S shaped features and stuff. I describe them in the book, and I have diagrams because it's all crazy and a lot of fun to learn about.
Yeah, awesome stuff. Thank you so much. Yeah, let's get into the questions here. So Luke asks, if you were to walk on Hyperion as a rubble pile, would the surface appear solid, or would you see cracks between the rubble pieces?
Oh, that's a good question. I don't know. I don't know. I think it would be well. We do have, for example, asteroids. We know that all literally all small rocky asteroids, or the vast majority of them, are rubble piles. If they get big enough, they can sort of become monolithic, like Ceres and Vesta. Those are not rubble piles; those are solid. But all the smaller ones that we've seen up close, and it's Eros, Didymos, Ida, all these asteroids that we've sent space probes to, they're all rubble piles. And when you get up close to them, you see that the surface. There's no place on the surface that is smooth. They look like construction sites. If you've ever seen where they dig up a thing and put all the leavings in a pile, and it's just rocks and garbage. That's what it looks like. In fact, for some of these missions, like Osiris-Rex and Hayabusa, the Japanese probe that went to Bennu and Ryugu. I knew I'd remember. These were designed to touch down on the surface and collect material. Finding a place that was smooth enough for them to hit without whacking into a boulder was really hard. And then the thing that destroyed me when they did this is I think it was Osiris Rex had a sort of a sampling mechanism on the end of a long boom, a long rod, and it was going to go down to the surface, and that thing was going to hit the surface, and then the probe blasted out cold nitrogen gas to reverse course and go out. It actually dug itself into the surface. The rocks that we see on these asteroids are incredibly friable. They're very fragile. Your typical snowball has more structural strength than these rocks. If you were to have one in your hand, you could crush it easily. The only reason they exist is because there's very little gravity on this asteroid. And so, yeah, Osiris-Rex buried itself like half a meter deep into the asteroid before it backed back out. If it had not backed out, it probably would have gone right below the surface. And I write about that in the book on the asteroid chapter. It was the most fun thing to write about, that if you landed on an asteroid, you have to be very, very careful to bury yourself. So walking on these moons would be very difficult. And I don't know. Hyperion is much larger, and it's ice, not rock. So I don't know if the ice would eventually fuse, and so you get kind of a thin crust on the surface, or it would certainly be very bumpy. But it's almost certainly not very smooth. And so it just, yeah, it would. These places are so alien, and it's so much fun to think about. Because you never hear this. And this is what kills me. How has nobody written about this before? And I think it's because we're so used to seeing images through our telescopes, images through space probes, that the idea of standing on one of these things and actually trying to walk around or do anything, it's just not something that comes naturally. So it was super fun to think about this stuff and write about it.
Definitely. Yeah, your book opens up with like the moon and even basic stuff that we should just know it automatically, like the day is 2 weeks long and the Earth just sits there in the sky during that time. You don't think about that stuff, and it's kind of interesting to envision that and imagine it.
A lot of people, and I'm going to run long, I know. I'll just very quickly. A lot of people ask me, what was the weirdest thing or the thing that surprised you the most researching this book? Because it's filled with facts. There's thousands of different things in this book. And I always learned that the Earth is in one spot in the sky from the moon. I also knew that the moon librates. It rocks back and forth, right? You can see a little bit past the east side and the west side. It also nods a little bit north and south because its orbit is tilted. Now, I talk about this in the book. Of course, that means that if you were on the surface is moving relative to the Earth. The Earth actually moves in the sky. Now, I knew that, but I thought it was just a little bit. And then when I tried to calculate it, and it turns out it's really hard to do that trigonometry. I wound up using stellarium online, and the Earth moves like 15 degrees. It makes an ellipse in the sky 15 degrees across. I think that's right. So if you were on the edge of the near side and the far side of the moon, you actually could see the Earth rise and set a little bit. It would go up a little bit and set a little bit, and go and do that every month. So we can always say that the Earth is fixed in the sky, or the Earth never rises and sets. It's not true. Not true. There you go.
Very cool. Awesome.
Okay,
Also,
off my soapbox.
very cool. Yeah, that also reminded me. We had Kelly Wienersmith on a couple of months ago talking about A City on
Really?
Mars. Yes, and that chapter kind of reminded me of that book. Did you collaborate on that at all?
Kelly and Zach's book, A City in Space, A City on Mars.
Yeah.
Yeah, so this is Zach and Kelly Wienersmith. Zach is the cartoonist who does Saturday Morning Breakfast Cereal, which you should all read. Very funny, sciencey, not always science, but very intelligent webcomic. Kelly is a biologist who studies parasites, of all things. And they've collaborated on some fantastic books like Soonish, 10 Technologies That Are Around the Corner. Very, very funny books, very interesting science. And they wrote one called A City on Mars. If you didn't see that talk, I'm sure it was great. Kelly's a wonderful speaker. They're both very funny. Talking about exploring space and how we don't really understand how to do that yet. Despite people spending billions of dollars, we don't know how to live in space. I didn't collaborate on the book so much as the first couple of chapters they sent to me while they were writing them and said, what do you think? And I said, well, blah, blah, blah. So I helped them with it. So I'm listed as an advisor, as a an acknowledgement in the book. Soonish as well, because they have a chapter on space elevators, building literally a tower that goes into space. And I'm like, nope, that'll never work. And here's why. And so they basically interviewed me for that book as well. Now, I've known both of them I've known Zach for almost 20 years now. And it turns out now I live near them. They also live in rural Virginia. And so that's kind of fun. I used to live in Colorado and never got to visit friends because I didn't have that many old friends out in that area. Now I do. So it's very happy. I'll be seeing them this weekend. I'm very excited.
Oh, cool. Small world. Cool.
Yes, it is.
Yeah, let me get through these other questions here. Richard Wright asks, if you were floating above Saturn's atmosphere, what would your weight be? I would think it would be many times the gravity if you were in a balloon over the Earth.
That's a great question. And it turns out, no. Gravity, just in general, right, depends on two things. It depends on the mass of the object that you're feeling the gravity from and how far you are from it. So a more massive object has more gravity. The farther away you are from it, the less gravity you feel. Now, the gravity you feel on the surface of an object depends on how massive it is and its radius, basically how big it is. And it turns out the way it works is when you do the math, it's a little bit different. And it turns out that the mass is important, but your distance is even more important. I guess that actually makes sense. But when you do the math, you realize Saturn, although it's much more massive than the Earth, it's much less dense, it's much bigger. And when you calculate, you do the actual math, you find out that Saturn's gravity, its surface gravity, I want to say, is 5% higher than Earth's. It's not much at all. Of all the planets in the solar, besides Venus, of all the gas giants, certainly in the atmosphere of Saturn at the tops of its clouds, it's the most Earth-like conditions. So if you were in a dirigible floating above Saturn, you'd weigh, 5 to 10 pounds more, depending on how much you weigh now. Not very much. It would feel very Earth-like. You would just feel a little bit heavier. That's all. Yeah, it's strange, isn't it? But that's the way the math works out.
Yeah, and the book's full of stuff like that, which is so cool. William Castro asks, what was the biggest surprise or unexpected thing astronomers have found out about Saturn and its system recently, say in the past 50 years?
Whew. The most, I don't know, right? There's a million things. The geysers on Enceladus is just a huge one. The lakes on Titan, another huge one. I don't think anybody expected that. And with the Cassini images, they could tell by how dusty the rings are, how old they are. And by measuring how they're raining down on Saturn, how much longer they will last. Because in some point in the future, they're just going to all fall down onto Saturn. And so a big surprise is that the rings are young. And I think the sort of average date they get is 150 million years. So I'm not sure about that number. So again, if you were a Jurassic dinosaur, you wouldn't have seen rings, and if you were a Cretaceous dinosaur, you would have. But all of these stories. I remember I just read a science fiction story about an alien that enters our solar system like 2 billion years ago. And the alien notes, wow, what a gorgeous planet with those giant rings. And it's like, well, maybe not. On the other hand, the solar system's 4.5 billion years old. And if the rings are 100 million years old, that's a kind of a coincidence that we happen to be looking at them when it has these rings. It's possible that this happens over and over again. That you make a ring system and it goes away after a couple 100 million years, and then two moons collide again, and boom, you get another ring system. Jupiter has rings, Uranus and Neptune both have rings, but they're much, much thinner than Saturn. Saturn has conditions that are really good for making big, thick rings. So yeah, I think that was a big surprise, and that was thanks to the Cassini data, mostly.
Thank you. Bill also adds that he enjoyed your book and wants to know if you're thinking about writing a sequel.
Oh my gosh, thank you. Yeah, that was one of those brilliant ideas. Like, gosh, if this book does well, I can write another one with different things. And I made a list of all the stuff I could write about, and then picked my 10 favorites. And some of them were easy, like Saturn and the Moon. I switched a couple later on. I added Pluto because I realized Pluto would it's more fun than you think. Visiting Pluto was very interesting. Now that we have close-up pictures of it, it was pretty cool. But then I'm struggling because in broad terms, what if I've done all the planets in the solar system that are different enough, right? If I write about Venus, I could probably get away with that. Mercury, maybe, but it's getting 8,000 words about what's interesting about standing on Mercury is not that easy. The other gas giants outside of Saturn, they're not different enough. They're all cool, but they're not different enough. And I talk about gas clouds and I talk about star clusters, and I'm like, well, you could be in intergalactic space. That would be kind of cool. There's a lot of stuff to talk about there. But coming up with a book length, 10 chapters, 80,000 words, turns out that's tougher than I thought it was going to be. And in some cases, it's just hard because a black hole is different than, say, a neutron star, and I could write about a neutron star and even a white dwarf, or maybe one chapter that covers both. But coming up with 10 really different chapters is tough. So I'm thinking I might do some writing and do it outside of sort of the publishing industry, and maybe write a series of things about it. I don't know. I haven't decided and publish it myself. I don't know. I will say that I have pitched another book to some publishers, a totally different book, completely different. And it's being pitched right now, and I haven't heard back from any publishers yet. We're still, it's still being shipped out. So we'll see. And if they don't accept that one, I'm gonna have to come up with another one because I do want to write another book. But even if I get a publisher to say yes today, it won't be out for probably 2 years. That's how long it takes to get a book out. I take a year to write it and then a year to publish it.
Well, we look forward to it, whatever it is.
But thank you.
Thank you. Combining a couple from Tony here. Tony notes that he just ordered your book and can't wait to read it. And
Awesome. Thank you.
yeah, he also has a question. He read that possibly water exists under the surface of the methane lakes on Titan. Is that true? I hadn't heard that.
I don't know if it's under the methane lakes per se, but there is an idea that Titan does have liquid water under its surface. It's so cold on the surface of Titan that water, you've probably noticed, like if you have a glass of water and you put ice in it, the ice at first is hard, but once you start to drink the water and the ice starts to melt, it gets softer. It's hard to crack ice with your teeth when you first get it out of the freezer, but later on, it's easier to crack. The colder ice is, the harder it gets. That's true of any sort of solid. And on the surface of Titan, water is frozen so hard that it has the same hardness as granite on Earth. So, if you had a boulder made of ice, water ice on Titan, you would need a hammer, a pickaxe, to get chips of it out. But because, again, there are internal forces on Titan, it may be warm just geologically, just like Earth is, because it may have heat left over from its formation and radioactive material in its core that heats it. There's this idea that it might have lakes or oceans of water underneath its surface, just like Enceladus and Europa. Interestingly, and this is fairly recent, that may be the rule rather than the exception. Water ice is extremely abundant in the outer solar system, and now a lot of moons of Saturn and Jupiter, Uranus, Neptune, and even some Kuiper Belt objects, it's possible. Pluto, that heart-shaped feature there at the bottom right, Sputnik Planitia, Tombaugh Regio, is a lake, or it's frozen nitrogen, but it's gooey. It's kind of like toothpaste consistency under the surface. Not clear why Pluto is still warm in its interior, but it's possible there's liquid water under Pluto, and that's nuts. It's 4.5 billion kilometers from the sun. It's 3 billion miles out, and it may have liquid water on it. And it's just that, it's just weird to think that there could be that much liquid water in the solar system. We used to think didn't I give my Strange New Worlds talk here last time?
Yes, that's right.
Yeah, about how there could be liquid water on tons of moons out there. So yeah, it may be the rule, not the exception for bigger objects.
Luke has a very similar question, so let's cut to that. He's reading that astronomers think the lakes of Titan are liquid like water, and others think they're more viscous like tar. What do you think is right?
Oh, I don't know. That's way above my pay grade. That's complicated. It wouldn't surprise me either way, except I'm not. I'm not a material scientist. I'm not a geophysicist or anything like that. I guess you could probably be able to tell. Well, first of all, you could do it theoretically. How cold it is on Titan. You know what the atmospheric pressure is. You know what raw materials you have, and sunlight hitting it, and you just simulate that in a computer. You know all the equations. You run the equations and see what you get for a viscosity. There are other ways. There are waves on the lakes because of the wind blowing. We see motion. As Cassini passed by Titan multiple times over the dozen years, and there are structures in the liquid like islands that change shape, and that's probably because the level of the liquid is rising and falling, perhaps. And you might be able to figure out the viscosity from that. Plus, there are all those tributaries and creeks and rivers, and the width of those would have to depend on the viscosity as well as the material that it's grinding through. But that might be a way to figure that out as well. So I don't know. That's a really good question. So I will say I don't know. There are people working on this, and I imagine just like anything else, when you have two sides of an argument, they will gather evidence and try to figure out who's right. And that's really cool. I never really thought that it might be really gooey, but I don't see why it wouldn't be. That's
Yeah, and
cool. I didn't know that.
yeah, and this ties right into our next question from Jeffrey. Maybe we can go there and find out. He wants to know if you have any thoughts about the Dragonfly mission for Titan.
Oh, do I love Dragonfly? Um, this is a quadcopter, so it's big. All right, so Ingenuity was the helicopter on Mars that Perseverance, the rover, dropped, and then it flew around until what was it last year, and it apparently tipped over, and the blade hit the ground and broke the blade, and now it's just sitting on the surface. Um, Mars has a very thin atmosphere and lower gravity than Earth. But because the atmosphere is so thin, those blades had to be huge. But it worked. It was a test bed. It was an engineering test to see if we could do this, and it did. It worked really super well. They thought it was going to fly like maybe 5 times, and it flew like 50. Typical JPL, hugely over-engineered. Dragonfly is a much larger mission that has been given the go-ahead. It's being built. It's going to launch in 29? No, 26? In the next few years, it's supposed to launch to Saturn. It's like a 10-year journey. Saturn is so frickin' far away. And it's going to drop down onto the surface of Titan, which has also been done. The Huygens probe was a probe on Cassini, and even before Cassini got to Saturn, that came off and fell to Titan and landed on the surface and took images. It was used batteries for power because there's nothing else they could power it with. The batteries lasted like an hour and a half or something like that and took images of the surface. Pretty cool. So we've done that. We know how to do that. And Dragonfly is going to soft land on the surface, deploy, and those rotors don't have to be nearly as big or move as quickly as the ones on Mars because the gravity on Titan is lower and the atmosphere is way thicker. You could almost fly on Titan. If you had big wings, you could probably flap hard enough and get off the ground. So yeah, that mission, I have friends working on that mission. It's super exciting because it's going to fly around and see Titan up close, which you can't do from orbiting Saturn. It's not even like Cassini orbited Titan. It was always flying past it. So it took snapshots from far away. So you see big things, but not little things. And Dragonfly is going to see these things up close. I just hope I'm around in whatever how many years that I get to enjoy seeing those for several years because that's just going to be phenomenal. That's going to be a dream come true. I can't wait.
Yeah, we'll have to stay healthy for sure. Cool. And I've been saving this last one for last. It's going to be a heartwarming one. So this is from Ember B. Starts off saying, I wanted to say I'm a big fan. I've been watching your crash course videos since my middle school science courses, and it really inspired me. And now I'm studying astrophysics in college.
Oh,
That's cool.
wow. That's
Yeah.
amazing. Fantastic. Congrats.
Yeah. And
We're in college?
Amber, go ahead and come off of mute if you want to answer that directly.
I'm at Seminole State, actually.
Which one?
Seminole State. Sorry, my
Seminole State.
microphone's
Yeah,
bad.
sure.
Yeah.
Okay, cool.
hmm
Yeah,
Do you
Amber,
know
do you
what
want to
you're
ask your
studying?
question? Oh, go
Oh,
ahead.
yeah, I was gonna ask, how did you get into science writing? Because that's my dream career. Or like, do you have any tips for getting into that sort of field? Like,
Yeah, just do it.
just
Just
do
do it.
it.
Um, I started writing in college and grad school, and it was while I was in grad school, like my let's see, like my second or third year, something like that. The web was invented. The World Wide Web came out, and you could write web pages, and that was brand new. And I started writing that um, and having fun with it. Um, and I realized I wanted to write more. So I thought if I want to write a book, I should write for magazines. So I pitched to Astronomy Magazine and wrote Under Alien Skies, that article I mentioned. Um, and just did it. I just, who's going to stop me? The web is open to everybody. So I created a website at my university and did it. And that's all you really need. Writing is one thing. There's also, Instagram and TikTok and all of that. And I have lots and lots of friends who make videos and just talk about the news. And I have a TikTok account. I don't really use it. I've made one TikTok, and it's about potato chips because that's who I am. But I have friends who are astronomers. Some of them aren't, but they just it's incredible. 2 or 3 days after some news comes out, and they've got videos where you see them and the pictures in the background. I have no idea how they do that. I got to learn. And it's one thing I absolutely love about this is that it's mostly women doing this. It's mostly young women, and that just wasn't true when I started out. It was mostly men, and for some reason, and it could be a selection effect. It could just be because I just follow more women, or they follow women, and when I follow them, I see who they're following, and I follow those people. And we all know the headwinds that women face online. It's much harder and it's much more difficult to get out there. And yet, I'm seeing so many women doing this. It's so fantastic to see those old intolerances falling by the wayside. So yeah, I would just say, get on social media. I imagine you probably already are, and just do it and follow people who do it a lot. See what they're doing and think, how can I do this differently? Not necessarily better, but just different, and to make yourself separate from everybody else, and just keep doing it. I sucked when I started, and now I'm brilliant. No, I mean, it's just that you get better over time. It's with practice. I mean, I write on average a couple 100,000 words a year. And now it's like I just wrote something today that was over 1,000 words, and it was super easy. It's just a groove you get into when you do it enough. Let me be careful here. That's not true of everybody. It's true of me, but it's like there's some things you do that as you do it more, you get better. And so just stick with it. It can be discouraging at first, but stick with it. And if you like it, keep going. It's possible to earn money doing it. Not easy. And you can still do it even if you become a professional researcher. So good on you. Stay in school and get out there and talk to people about science, because it's so much fun. So much fun.
That's awesome. Thank you so much.
You're welcome. Thank you.
Oh, wow. I can't think of a better way to end. So, thank you so much, Phil Plait, for spending your evening with us here tonight. It was a great talk, and we all really enjoyed it. And yeah, we hope to have you back again in the future.
My pleasure.
All
Thank you,
right.
everybody. Thank you very much for inviting me.
Thanks so much. I'll let you get back
All
to
right.
your evening. But everyone
Bye.
else, bye. But everyone else, stick around. No going anywhere because we have more for you tonight. Got some club news for you up here next. So let me commandeer the share screen.
Okay, I turned it off, so you're good.
Cool. All
All
right, there
right.
we go.
Bye.
Bye. Thank you. All right, so yeah, our big news. Hopefully, this is showing up. I think it is. We got a new website, people. Thank you, Rob Fleming. Rob volunteered his time as a professional web designer to give CFAS.org an overhaul, and it is awesome. So thank you so much. Head over to CFAS.org, CFAS.org, to check it out yourself and tell your friends. Let me see if I can actually switch my screen here and show you myself. Doot. Look at that. It's beautiful. Like, and like things happen. Like it's dynamic and stuff. Like I love this so much. Thank you, Rob. This is awesome. We've like been dragged into whatever year this is. But yeah, it's actually got a lot more information in it too. So in addition to obviously, being able to sign up for new memberships or renewing your memberships, also highlighting some of our great speakers like the one we had tonight. And if you want to go back and watch some recordings of our earlier speakers, you can explore more speakers there and go through the entire archive there. There's definitely lots of good stuff. Also, we have a gallery here of some of our astrophotography from our members. That's beautiful as well. You can see more there as well. And if you want to add to that yourself, just let me know. Send me a note. It's pretty easy to add stuff in here and show that off to the public at large. Just a reminder, the CFAS.org website is really intended for people outside of the club who are thinking of joining. and there's a contact form for them as well. And up top here, we have a navigation. It goes even deeper. If you want to get some merch, hit the merch button. That'll take you off to our Redbubble store. Events, we're stay tuned. They're coming. Um, Also, that astrophotography gallery, more on the speakers. If you want to get into outreach, if somebody wants us to support a program for going out to a school or whatnot, that's the new place for doing it. And that will go off to our outreach coordinator, Douglas Woods, automatically. And if they want more information about membership or to see the beautiful faces of our board of directors, that is under the membership tab as well. We'll probably rename that to About or something soon. But thank you, Rob. Really appreciate it. I think you're on tonight too. So great job. That is so cool. Let me go back to my slide deck. Yeah, so in other news, our next in-person meeting will be in September at the planetarium. We don't have a date for that quite yet. The board will be meeting next week to nail that down, but stay tuned. Historically, we have not done a August meeting because most people are out on vacation and the weather's terrible. We'll see. If I can get an awesome speaker, maybe we'll do one anyway over Zoom, but stay tuned. Also, officer elections are coming up in October, and we have to start thinking about that as a board. We have, for example, Denise Woody's term is up as secretary, and we got to fill that slot. So if you're interested in serving on the board of directors, please let me know. And like I said, we do have a board meeting next week over Zoom on Wednesday night. So if you want to sit in and just see what it's all about, shoot me a note at president@cfas.org and I can get you hooked up. And thanks to our board members and all of our volunteers who help make this club as awesome as it is. You may not realize it, but we're actually one of the biggest astronomy clubs in the country and one of the best ones, if you ask me. Y'all should be proud. In other news, it's summer. The nights are short, the weather's crappy, but let's make the best of it. We actually have some outreach happening regardless. So Astrofest at the Orlando Science Center is coming up on July 20 to 21st. Obviously a solar observing event. Also, we're booked out. So into November for Forever Florida and Goldsboro Elementary have already tapped us. We even have stuff booked out in 2025, but I won't get into that quite yet. We're popular people. If you want to get involved in outreach, that involves going out to these events and bringing your telescope and just showing people things like Saturn for the first time and capturing their imagination. Contact outreach.cfas.org. That will go to Doug Woods. Or just go to cfas.groups.io/g/outreach. That's our subgroup for outreach on Groups.io, where you'll get notifications of all the upcoming events and you can talk amongst yourselves as to how you might want to support those. So do get involved. It's a very rewarding activity. Speaking of outreach, looking back to June, we had one event, despite the weather, the Orlando Science Center Science Night Live, and also, there were two events, also the Altamont Springs City Library. And people I know of who supported that include John Frank, Christian Nunez, Sam Selig, Margaret Selig, Will Okendo, and Doug Woods. So thank you, all of you, for spreading the word of how awesome the cosmos is. And if I missed anyone, I'm sorry, but you're awesome too. Upcoming astronomical events. It is summertime. The good thing about summertime is that the summer Milky Way is out. So if we do get a clear night, take advantage of it. There's some awesome targets up there, including the Dumbbell Nebula, the Veil Nebula, the Crescent Nebula, the Lagoon Nebula. These are all my favorites. And if you're doing narrowband imaging, these are like the most prettiest things in the sky you can see from where we are. So the other good thing is that if you're doing narrowband imaging, the moon doesn't really matter that much. So you have a little bit more flexibility and you can really be more opportunistic when the weather does cooperate. Also coming up on July 13th, just 3 days from now, the moon is eclipsing Spica at 11:48 p.m. So if the weather cooperates, stay up for that. It might be kind of cool to see. And a few days later, Moon and Antares will be making a close call within 3.5 degrees. Moon and Saturn coming within 5 degrees on the 24th. And then at the end of the month, we have a couple of really cool things happening. 29th to 31st, Moon, Jupiter, Mars, Aldebaran, and Pleiades will all be just above the eastern horizon at dawn. So if you're an early riser, go check that out. And the good thing about dawn is that it's more likely to not be cloudy. And at the very end of the month, we have the Delta Aquarid meteor shower. And that's normally a southern hemisphere thingy, but since we're in Florida, we can see it too. So if you do happen to see any meteors at the end of the month, you can feel extra smug about it because your relatives up north did not see them. And also, T Corona Borealis watch continues. Any day now, they say, it's going to pop. So if you want to see a nova, hopefully, I'm kind of hoping it waits until the sky is clear a little bit more, quite honestly. But keep an eye on Corona Borealis for a new star, because if you see it, you just spotted a new nova. You might be the first. Oh, Tony says he recently acquired a new Lunt Hydrogen Alpha telescope. Looking forward to showing attendees the sun at the Science Center in July. Thank you, Tony. And again, the CFAS board needs you. We especially need a secretary because our term limit's up on Denise. Thank you, Denise, for your years of service in that role. And hopefully, we'll talk about it next week at the board meeting, but I hope you're up for a different role. But we always need help on all of this stuff. So we're always looking for an extra set of hands. Again, these are volunteer positions, but if you want to help out the club and help us be even more awesome, you can be a part of that. So let me know at president@cfas.org if you want to get involved behind the scenes. And good way to get your feet wet is just sit in on our next board meeting on Wednesday night. We can make that happen. And with that, let's head over to our Astrophotography Showcase. And as always, if you're on line here, I will invite you to unmute yourself and describe in your own words what we're seeing. Let's start with John Pinto.
Mr. C-Star. Hey, Aaron Frank. Hello, everybody. Hey. So let's see, what are we starting with here? M23.
Yep.
So these are C-Star photos. Let's see. We've got M23 is about 2,000 light years away, and it is a fairly young open cluster. It's only about 330 million years old, so just a beautiful night sky image. And again, what I love about this is that's just 8 minutes of imaging time. So if you got any astrophotography equipment or you got yourself a C-Star, doesn't take long to have beautiful photos.
Yep. Doesn't matter how bright the moon is either.
Clusters are always a great target. Clusters are always a great target. Yep. As we see in the next one, this one, M19. So the other one was 2,000 light years away. This is 29,000 light years away. So a little bit further away, looks a lot smaller. But luckily, M19 is buried right in the middle of the Milky Way. So I get really nice background stars, which I love. And where the other one was young, 330 million years old, this one's really old, almost 12 billion years old, almost as old as the universe is. Universe is about 14 billion years old. This is, a lot of these stars were only 2 billion years after the start of the universe. So kind of nice contrast there, Frank, between the two targets. But again, definitely. 7 minutes with your C-Star and you get, beautiful, beautiful image to contemplate. Thanks, Frank.
Yeah, globular clusters are my favorite personally. They're ancient. They're like, some of them are captured cores of other galaxies, and there's even a chapter about that in Phil's book, actually, called "A Planet with a Million Suns." Globular clusters. The irony, of course, being there probably aren't many planets in globular clusters because they're very metal poor. But anyway, he addresses that. Isabel, I don't think she's online because she's currently in Utah on vacation. I don't have the view that I usually have of who's on. Yeah, I don't think she's here. But she did send some photos from Utah. This is from the Canyonlands region. She took this image of M16 using her C-Star out there. Gorgeous, gorgeous image. M16 being the Eagle Nebula. And if you zoom into the center there, you might recognize that as the Pillars of Creation that the Hubble Space Telescope made famous. And it's called that because that's a star formation region happening there in those little tendrils there. Gorgeous, gorgeous part of the sky. She also took a few nightscapes out there. So she took these just using her iPhone and nothing else. So iPhones are cool, but dark skies are even cooler. You can just snap a photo and see the Milky Way in such detail. That's pretty cool. And she's been playing around, adding some visual interest to the foreground. That's Isabel herself, I believe, there waving around to add a little bit more composition. And another trick you can do is grab a flashlight and do what they call light painting. So she probably one of her daughters or children just lit a flashlight on them while taking that shot. And that sort of illuminates Isabel and her husband in front of the Milky Way, which is kind of a cool effect too. And one last nightscape from her. And images like this are just so cool, right? I mean, like you've seen like these images of edge-on galaxies that we show here from time to time in astrophotography. This is what we're seeing here, like those gas lines that you see sometimes, those gas lanes along the edge of a galaxy. That's what we're seeing here in our own galaxy from within. It's kind of mind-blowing stuff, but very cool. Speaking of nightscapes, our own Richard Wright has an article in this month's Sky and Telescope I noticed on doing star trail photography and some tips and tricks on that. So thank you, Richard. Go check that out if you haven't already. Mark Femininio, are you here? don't think I saw you. I'm gonna say no. If you are, please unmute and holler. But this is awesome. This is a noctilucent cloud that was created by a SpaceX launch, shot from Oviedo. Oh, wait, I have a message here. Yeah. Well, thanks for the article, Richard. But how cool is that? Like normally you have to go to Alaska to see noctilucent clouds and be there at just the right time, but we can make our own here in Florida. So just send a rocket up there to the stratosphere, and the particles that get spread out there are noctilucent clouds, and that is absolutely, absolutely gorgeous. So thank you, Mark, for sharing that image. Really? Luke says it was an apod. Oh my gosh, you're kidding me. That's awesome. It really was. Oh yeah, it's a similar one. So that's not the same photo, but yeah, that one's by Pascal Fouquet. So somehow they both got the same image, but from a different spot. Very cool though. Barbara Harris, I think you're here.
Yes, I'm here.
Yeah, tell us what we're seeing.
I want to do a shout out to Rob for the website. I think it turned out really nice. I'm impressed with the new website.
Yeah, me too.
Anyway, this is my annual image of Barnard star to demonstrate the proper motion of Barnard star. This is my 11th year. I take an image usually for photometry. So this particular image is 15 seconds that I in V filter. And then I start stacking all of those images from the last 11 years to demonstrate the high proper motion of Barnard star. So this is a project I started back in 2014, and I love doing it every summer to demonstrate that proper motion.
Is that actually the fastest proper motion of any star in the sky?
Yes.
Very
So
cool.
yes, it is the fastest proper motion. So from our viewpoint, that's the fastest moving star.
There's something reassuring about seeing this every year. Like, the universe is still ticking away. So thank you, Barbara. And you also have a cool shot of I never know how to pronounce it. Rho Ophiuchus.
Rho Ophiuchi.
There it is. Thank you.
Yeah, this is a target that I've wanted to do for years. But for us in Florida in the summertime, and it has to be available in the earlier part of the evening when it's usually rainy for us. But I think it was Saturday, we had an unusually clear early part of the evening, and I was able to capture, I think this is an hour and 20 minutes of the Rho Ophiuchi region. And it is with my Rokinon 135 lens and a QHY 268 color camera, 2-minute sub exposures. But I just love everything in this image. It's just so busy with astronomical objects. There's M4 there. There's the gases around Antares. So there, emission nebula, dark nebula. It's just a gorgeous area of the sky. And for years, I've always wanted to image, and hopefully I could collect more time on it and add to it. But I was happy with just the time that I had with it already.
Absolutely. That's gorgeous. And like you said, it's every kind of nebula in one there. And also, that's got to be the Milky Way behind it too, right?
Yes.
So much going on there and so much color. I love it. Thank you, Barbara. Oh, I got one too. This is M101, commonly called the Pinwheel Galaxy, but I think there's like 3 galaxies that are called the Pinwheel Galaxy. This is M101 though, the one that's near Ursa Major. About 20 hours of exposure on this one, and I'm happy with it. It's a bright galaxy, but it's deceptively difficult to capture because it has all these really faint arms and stuff going around on the edges there. Also picked up a little bit of a satellite galaxy there, a little irregular one there off on the right there. And you can also see some areas of red hydrogen gas. So there's also some hydrogen alpha exposure time in this as well, kind of highlighting the star forming regions, or what would be the nebulas inside that galaxy if you were in there, which is pretty cool if you ask me. This is shot with my usual gear, Skywatcher 190 MN Mach Newtonian telescope, on a Paramount Mighty mount and an ASI 2600 Pro camera. And
Frank,
last but yeah,
I just want to mention that there was a supernova in M101 last May, and I'm still monitoring it in B, V, and R filters. So I
oh,
think it's down to about 15th magnitude, but it's still visible in one of the spiral arms there.
oh, cool. I did not know that. I'll have to find that. Thank you.
Yeah, I'll send you a finder chart of where it's located, but
Appreciate
um,
it.
you should be able to pick it out still.
Yeah, definitely. That would definitely show up in here. That's awesome. Thank you. I love hidden treasures in these images, like you can pick out a lot of distant background galaxies and stuff, but a supernova, that's an extra special bonus. Thank you. And let's finish up with Wes. I save the goodest stuff for last. Wes, what do we have here?
Hey there. This was my M109, I think it was from earlier this year. This was the one that I did the PixInsight demonstration on, and
Yeah.
I think I tweaked it a little bit more after we did that presentation, but it's mostly what I ended up with. Um, this one, I was happy with it because this is a small galaxy. It's 63 million light years away, and it just made me realize how hard it was that Charles Messier and his friends, you know, how small of these things that they spotted, that little like nebulous objects that they pointed out. It's like, oh, there it is. Like how small it was and whatever gear they were using at the time. It just impresses me that like 200 and some years ago they were able to spot this thing, and it's still, even for my stuff, it's like this small and hard to make out.
Yeah, gorgeous stuff. You can really see the bar structure in the middle there too. Like it's amazing we can get that much detail in this thing. So nicely done. What's the total exposure on this? Remember, like 20 hours, right?
Around 21 hours, yeah, maybe
Yep.
just a little under.
Cool. And yeah, we are planning still another astrophotography workshop. I'm going to do one on narrowband, but I think I'll wait till more people are in town. There's a lot of people traveling right now, but I haven't forgotten people. It's still going to happen. And finally, the Seagull Nebula, right?
That's right. Yeah. IC 2177. I imaged this in February and March, but didn't get a chance to put it together until like May. So just now releasing it. And it turned out a lot better than I thought it would. I love the way that the color turned out. And I'm really happy with this one. And this one was pretty evenly, 8 hours of HA, O3, and S2. I didn't like gang up on just one of them. So it's a pretty balanced image. It's about 24 hours, a little bit less. So I really like this one. I like it how it turned out.
You should. I mean, I've tried this one myself, and I could not get that oxygen signal there anywhere close to how you did. So gorgeous, gorgeous thing. I don't see a seagull though. Looks more like a really happy goldfish. But
Yeah, you
anyway.
have to like zoom out. The seagulls are steep from like this part. Yeah, that's just like the head and its beak is open. If you
Right.
a wider field, it's more evident.
Cool. Gorgeous. Great work. Thank you so much. And yeah, I think that's it. So that's all, folks. So yeah, like I said, probably gonna skip the August meeting. We'll see. We'll see. If I get someone great, I'll let you know. But if not, we'll see you live in person in September. Again, stay tuned for details on when that will be. And thanks everyone for joining us tonight. I think it was pretty awesome. And as always, keep looking up. See you next time, guys.